Okay, here comes the final part of this run-through, Edexcel International GCSE for the Physics and Double Award students, January 23, paper 1P. Remember, 1PR is also available if I get requests for uploading it. Don't forget to like and share the videos that you've watched so that the videos are seen by more people and it helps with the YouTube algorithm. So I think we've only got one more video to do. It's the final part. So we're looking to do, I think it's questions 10 and 11 we haven't done. So in the previous video we did the astrophysics and the electricity. And I just want to show you that one more question where we did the microwaves earlier. And we looked at waves, question 6 and 9. This is question 9. They did an investigation on microwaves. And they took these readings because they were detecting how strong the microwaves were from a microwave transmitter. And then they plot it as a graph. And you see how many graphs there are in one exam. So I think this is the 4th graph up to question 9. And then in the next question, you're going to have to sketch a graph. So in this question, on question 9, what you have to do was to check whether the graph is inversely proportional or not. So sometimes you have to use the data provided in the graph and they give you an equation to check. This is quite a common method to see how good you are mathematically. Okay, once you've done a few like this, you'll see that you can just take 2 or 3 points from the graph and see if the multiplication equals what they're saying it equals to. Okay, so this is all the science skills. It's something you can only practice. You can't necessarily be taught every eventuality. They'll just give you something slightly different each time. Anyway, so the next part of the question is about heat, yeah? And topics 4 and 5, if my students will remember, that we actually did, at the beginning of year 11, we did a exam which covered topics 4 and 5 because the thermal part of topic 4, the thermal physics, heat transfer, of course, happens in solids, liquids, and gases. So topics 4 and 5 are often linked in exam questions. So question 10, it says a student pours a known volume of hot water into a metal container. So metal container, yeah, is the inner container. It contains the hot water. Now remember, metal containers, metals are good conductors. So they're going to probably ask you about conduction. So remember, the way you get marks is by using the scientific vocabulary in the depth and detail required and to make sure that you've explained your reasoning clearly. So depth, detail, clarity. I keep on repeating that to my students. So they place the metal container that has the hot water in it into an insulated plastic cup which contains an equal volume of cold water. So obviously what's going to happen, yeah, there's going to be heating, which is a transfer of energy, yeah, heating is a form of energy transfer from the hot water to the cold water. Let's put the cold water in blue because blue is, yeah, so the insulated plastic cup contains the blue water. So the heat goes from the hot water and the inside because a metal is a good conductor, yeah, that you're going to go until the temperatures eventually reach equilibrium or become equal. So energy transfer always happens from hot to cold. Hot to cold. So here is the hot and here is the cold. Okay, so heat is basically going to flow from the hot into the cold, yeah, and then there's no lid on it, so you might also see some heat escaping from the top, and that would be by evaporation. the most energetic particles will escape the surface and go into the air. They'll warm up the air, and then you'll get convection. And convection happens in fluids, liquids and gases. And that's where the heat has escaped, gets into the air above the water, and then the hot air will rise and take away the energy with it. So you need to be able to describe conduction, yeah? So conduction is normally solids, and then you've got to also be able to describe other forms of energy transfer, okay? Okay, so back to the question. The student uses temperature probes, so electronic thermometers if you like, to measure the temperatures of both the water, which is hot in the metal container, and the water in the plastic cup, which is the colder water. Okay? So you need to measure both thermometers. And then it says the hot water has an initial temperature of 70 degrees centigrade, and the cold water has an initial temperature of 5 degrees centigrade. Okay? So maybe it's taken out of the fridge. And then what they want you to do is to draw a cooling curve and a heating curve. It says, on the axes below, sketch how the temperature of the hot water varies with time and the temperature of the cold water varies with time. Well, the hot water will cool quickly at the start, so that'll be a cooling curve. It's going to curve because at the beginning, the temperature is the hottest. The temperature is the hottest at the beginning, so the rate of energy loss is going to be steeper at the beginning. And gradually, when it reaches closer to the temperature of the cold water, the rate of transfer of heat, yeah, the rate of change decreases. Okay? So the bigger the temperature difference, the bigger the rate of change. The smaller the temperature difference, the slower the rate of change. So this is just mathematics. So the rate of change decreases, and that's why it's a cooling curve. Okay? Now, on the other hand, in the colder water, so the cold water starts from down here, minus 5 degrees, what is lost from the hot water is gained by the cool water. Okay? So the cool water doesn't have a cooling curve, yeah? The cool water, the cold water will have a heating curve, okay? So it's going to heat up. And the rate, because they're equal masses, yeah? They told you in the question that they got the same mass of hot water in the metal container and the cold water surrounding it. Because there's the same amount of mass, the rate of the curves will be opposite, yeah, the steepness. So what one loses heat, okay? So it will keep on doing that until thermal equilibrium is reached. So you get to a point where you have the temperatures becoming more equal. But they won't actually touch until they eventually both become the same temperature. And they'll eventually have to go to room temperature, because the room temperature is also another source of, or a different energy source, if you like, because it'll be room temperature will be around here, won't it? The room temperature will probably be around there. 20 degrees centigrade or something. Yeah? Say 22 degrees centigrade will be the room temperature. So eventually they'll probably both go down. So probably I haven't drawn it quite accurately. Probably might go there. And the red one probably will eventually, oh, I haven't drawn that very well. Let's get rid of that one. And the red one will probably go closer to the 22 degrees centigrade. So they'll both eventually move towards 22 degrees centigrade. Okay? Hope that makes sense. And you get 4 marks for this question, and we'll look in the mark scheme. Okay? Now the key point here is the amount of hot water and the cold water is equal. If the cold water was much lower mass, it would heat up much more quickly. The lower the mass, the less energy it takes to heat up. Yeah, so big mass requires more energy to heat up. All right, so here's question 10, and these are how they're marking it. The line decreases from 70, I got that. The other line increases from 5, 2 marks. Both are correctly curved. One is a cooling curve, one is a heating curve, and the lines don't touch. They become what mathematicians call asymptotic. They get closer and they reach the intermediate equilibrium temperature. Okay? And of course, the intermediate temperature should be closer to the 5 degrees than the 70 degrees. It's not going to reach that hot because remember, room temperature, because of room temperature, is closer to the 5 degrees. So I should have drawn it with more going down to about 22 degrees, but I think I got all 4 marks. The next part of the question says, we're going to look at that in a minute, part B we haven't done yet. You've got to explain it, and here they get 4 marks for explaining what's happening, like I explained to you already. So we're going to have a look at it. Hot water loses energy and cold water gains energy. What kind of energy? Thermal energy. Okay, so it goes from one hot thermal energy store to another thermal energy store. Okay, and this thermal energy is transferred from hot, high temperature, to low temperature, from hot to cold. Okay, and of course it's because you have conduction through the metal, good conductor. And the idea, number 4, the idea that the energy transfer stops when the 2 temperatures become the same, when thermal equilibrium is reached. Now, when is that going to happen? We've already talked about it. It's going to happen eventually when they both get to room temperature. Yeah? As long as you say they'll both reach the same temperature. And they shouldn't cross. One of my students, I saw him writing it, and he'd crossed the lines. And the hot one's not going to get colder than the cold one. Okay? And then it says, some thermal energy is also lost to the surroundings. And I told you in my diagram, it can be by convection and evaporation. But also, there's always some radiation. Anything which has a temperature above absolute 0 will be radiating infrared. Some kind of electromagnetic radiation will be coming off any hot object. Any object with any temperature will radiate some of its energy. And of course, if it's hotter than the surroundings, it will give out more than it takes in. Okay, so radiation is a constant exchange of electromagnetic energy between objects, solids, liquids and gases, doesn't matter what state you're in. And then little or no thermal energy is transferred out through the plastic cup. Why? Because a plastic is a good insulator. Okay, so this is an extra point that they're accepting, that the plastic cup is actually reducing the energy transferred to the surroundings. Okay, so most of the energy transfer will be from the top. Okay, so we're going to look at that in a minute, and then part C is also here, yeah, and looks like part C is talking about convection and radiation. So we'll have a look at the question, and again the idea that equilibrium temperature, yeah, is reached, yeah. So we'll have a look at what they're actually talking about in part C. So part B, we've already looked at the answer. Here's a question. Explain why the temperatures of the hot water and the cold water change. Well, we already explained all that. And the way this is where you get the level of depth, detail and clarity. And it tells you, make sure you refer to the different types of thermal energy transfer. Now, what are the different types of thermal energy transfer? That means you should involve conduction, convection, radiation, and in this case, evaporation, because a hot source of liquid will be able to evaporate. Okay, so we've already gone through it. So here are the points. Hot water loses, cold water gains energy. What kind? Thermal. Thermal energy transfers always from the hot place to the cold place, in this case water. Metal is a good conductor. That allows you to talk about one type of these thermal, one type of different thermal energy transfers. So the conduction will continue until thermal equilibrium is reached. We talked about that. And other points you can make are here. Some thermal energy is transferred to the surroundings, like I drew in the diagram, by evaporation and radiation. Okay? So it's basically the hot water especially will radiate more than it absorbs by radiation. And then the final point that they were making was that the plastic cup reduces heat loss to the surroundings, and that was a good one to use. It keeps the heat inside for longer because it's a good insulator. Okay? So it reduces heat loss by conduction. So we have in our answer mentions conduction, we've mentioned convection, mentioned radiation, and mentioned evaporation. Now, there's 6 bullet points for 4 marks. Any 4 from my list or from the exam list will get you the 4 marks. Now, all it requires is for you to use the correct scientific vocabulary. And that's what you should be practicing between now and May when your exam is. So you're in your last 6 or 7 weeks for paper 1. Okay? You should have already made all your notes, and you need to know what technical vocabulary you should be including. All right, so the next question, the final part's part C. What does it ask? It explains, wrong method. I want to highlight it. Explain how placing a lid on the plastic cup would affect the results. Well, we just said a lid, yeah, especially if it was plastic, would be a good insulator, and it would be, if it was airtight, it will reduce heat transfer by convection. So if you have a tight lid, yeah, will reduce the heat transfer by convection, which will stop heat rising out of the container. So basically, you're trapping the air inside, so it maintains the heat for longer. Yeah, it will also reduce the heat transfer by radiation or evaporation. So the lid's there, obviously, it will still be able to evaporate, but it's going to hit the lid and then condense back. There will still be some energy loss due to evaporation, however, but it will reduce the rate of heat transfer. Okay, so you could actually put here, reduce the rate, how fast of heat transfer, to be more precise. And then going into the answer, second part, so equilibrium temperature will be higher than without a lid. Okay, it will maintain more heat inside. Okay, and the time taken to cool to room temperature will also take longer. Okay, it will eventually cool down, just like anything, even in a thermos flask. If you leave it long enough, the heat will be able to escape. There will be ways for it to escape. And here is question 10, and we've done another 11 marks. There's only one question left to do, and then you'll see it's linked. So this is mainly on solids, liquids, and gases, and mainly on the kinetic theory of gases. Okay, so this comes from topic 5, which is solids, liquids, and gases, but the main focus is on kinetic theory. Kinetic means movement, okay? So we're looking at what happens. Diagram 1 represents the atom as a gas in a container. Okay, now you can tell it's a gas because the atoms are far apart. Explain how the atoms exert a pressure on the walls. Okay, well, what are these atoms doing? These atoms are whizzing around randomly. They're whizzing around randomly. So this one might be going that way. This one might be going this way. This one might be going this way. And this one might be going this way. And they keep on colliding. So this would be a good way of actually putting it into your diagram, adding the arrow to show the velocity vectors. So now you can say in your answer that the atoms collide with the walls periodically. Yes, they keep on colliding. And collisions are effectively forces exerted on the walls. And of course, if there's forces constantly hitting these walls, like this one, the combination of all these mini collisions with these atoms is what pressure is. Pressure is the total force, the sum of the forces of the collisions, divided by the area of the walls. Okay? So that's how pressure is exerted. Okay? Atoms exert pressures by collisions. So the key words you want to include in your notes is collide, forces, collisions are equal to forces, and force per unit area. Okay? That's what pressure is. It's a microscopic understanding of the molecular movement or atomic movement or particle movement. Okay, next part. It says, explain why the pressure of the gas decreases as its temperature falls, as its temperature decreases. Imagine it was a hot gas and then it cools down by heat loss, like we talked about in the last question. It says the volume of the container does not change. So why are they telling you that? Because it's a controlled variable. They don't want you to, remember we did Boyle's law, which is pressure and volume. Well, this is actually the pressure law, yeah? Whereas pressure and temperature. Remember that temperature always, in kinetic theory, should be related to the absolute temperature scale, which is in Kelvin. So, how do you explain why the pressure drops when the temperature drops? Okay, so the atoms will move more slowly at lower temperatures. So if they're moving more slowly, they will collide less often. Yeah? So the rate of collisions will decrease, or less frequency. Yeah? So you can also mention the rate of collisions. So the rate of collisions is a key term, means number of collisions per second. So you've got to be scientific. So frequently means how often they're colliding. And then the next bit, it says the total force, therefore, on the walls decreases. And each collision also will be less forceful if they're hitting the wall more slowly. So they hit the wall less often and they hit the wall with less force. So the pressure will decrease. So you could even add that in. So pressure will decrease. I've just done it in bullet points, and I think that's fine to do that as long as you show that there is clarity in your communication. Okay, so the next part, part B. The diagram shows a device called a magneto-optical trap. Don't worry about it, they're just making up some terms. So it's a magneto-optical trap. Optical because it's got laser beams in it, and magnetic because there's a magnetic field produced by these coils. They're not going to ask you anything about the magnetic field. But it's a trap because in the middle, they've trapped some atoms magnetically. That means they must be charged. Okay? Remember, hot gases will usually be in a state called plasma, where they've been ionized, so the electrons have escaped. It says physicists used this device to cool gases to extremely low temperatures. Okay, you do not need to know how. Okay, and then they're telling you what I just told you. The MOT, magnetic optical trap, uses laser beams and magnetic fields to trap a small collection of atoms in the middle with extremely small kinetic energies. So they actually want to bring them down to very low energy. Before I was talking about high energy, so I may have confused you. So they want to make the atoms inside here very low temperature. Okay, and then here is giving you some maths. Each trapped atom has a very low mass, 10 to the minus 27 kilograms order. So this is the mass, and has a mean speed of 73 meters per second. All right, so the mean speed is v with a bar on top of it. Bar on top means mean speed. Now, if you know the mass and you know the speed, you can also work out the mean kinetic energy. And maybe that's what they're going to ask us. They then want you to calculate the temperature of the trapped atoms. And they're going to give you some help. They're saying that if you know the mean kinetic energy of an atom, it's directly related to the temperature in Kelvin if you multiply temperature in Kelvin by this number. So they're giving you an equation, just like they did in that question on the graph in the previous question. They're giving you an equation and they want you to use their equation. And it's not a known equation in GCSE. They just want to see how good you are mathematically. Remember, questions 10 and 11 are the end of the exam. In this case, it's the final of the 110 marks. And it's the final 4 marks. So they want to see who can cope with mathematically difficult numbers and mathematically difficult, more challenging questions. So remember, the mean kinetic energy, we know the mass and we know the mean speed. We can just put it into the kinetic energy equation with the data they've given us and work out that half of the mass, there's the mass from above, times the mean speed squared will give us the mean kinetic energy. So when you do that, you'll get a value very small in joules, 1.33 times 10 to the minus 23, if we put it just to 3 significant figures. Okay? Then we know the mean. Now we know the mean kinetic energy. You can put the mean kinetic energy into this equation. And that's what I've done here. I put it into the left-hand side of the equation, and I put their number multiplied by the unknown temperature on the right-hand side of the equation. So the only unknown is the unknown temperature. Now, if I change the equation around, you'll see the temperature can be calculated by these two standard form equation numbers, and you'll see that the temperature will basically, 10 to the minus 23s actually cancel out. So you can just divide 1.33 by 2.1 and you'll get a temperature to 2 significant figures of 0.63 Kelvin. That's only 0.63 above absolute zero. Remember, it's in Kelvin. Okay, the coldest possible temperature is minus 273. So this is minus 272.5, roughly speaking. Well, that's the end of this run through. I hope you found it useful. And please make sure you show support and like the channel, like the video, give it a thumbs up and share it with anyone else who you think will benefit from it. And I'll put more videos once you comment and you have shown enough students are following the GCSE videos, because obviously I also have A-level students, and A-level students tend to request more papers. So I don't have enough time to do them all, but if you're asking for them, these ones are the ones I've done with my students. So only 23 and maybe 24 I'm going to upload. Okay, but obviously the more demand there is, more likely I am to do it sooner rather than later. And we're in the last 6 weeks. All right, so the next, here's the mark scheme. So 11A, you can have a look at it. Yeah, atoms colliding with the walls, forces exerted during each of these collisions, and pressure is the sum of the force on the area. Yeah, because pressure is force over area. Okay, and then if the particles move more slowly, they collide less frequently, rate of collision is reduced, and therefore the force on the container decreases. And again, pressure is force over area. So that's how you're relating it. And then the final part of the exam was using their equation to work out microscopic kinetic energies of particles, yeah, to getting it right, and then rearranging the formula that's given to be able to work out the temperature in Kelvin, which I showed you. And here is their answers and what you're getting. So you get one mark for this, 1 mark for this, 1 mark for that, 1 mark for that. So thanks again. Hopefully see you in the next video. Hopefully there's lots of likes this time, and the video's a success on YouTube. And if you want me to do the other January 23 paper, leave me a comment. Bye for now.